In this video, we're going to talk about how we can use density as our standard of measurement when using our homemade mass balances. But first, we want to understand what density is. We talked about units of measurement and standards of measurement in a previous lesson. And more importantly, we talked about what standards of measurement were and how important they were to the study of chemistry. First, we want to understand that density is a derived unit of measurement. A derived unit of measurement is when we combine already standardized units of measurement in their basic forms. Remember that mass is a SI base unit of measurement. When we talk about the kilogram, we're specifying a standardized base unit of measurement. And we would symbolize that as little m in an equation when we're speaking of mass. We also know that volume has a standardized base unit of measurement. In the metric system, that tends to be the liter that we see used often. The SI system uses things like cubic centimeter and cubic liters. So what we often use in chemistry is the metric system over here in the United States. But when we combine units of measurement, base units of measurement mathematically, like with division, we would get what's called a derived unit. So when we divide mass by volume, we get a new unit of measurement we call density. And that is a derived unit of measurement. So density we could consider a unit of measurement all on its own. But we need to understand that the way we get density is by dividing mass by volume. And that's what density is. Now there's something very special when it comes to water's density. And we can use this special quality of water's density to our advantage. We understand, and we have demonstrated through experimentation, that at room temperature and pressure, which is what we commonly work at in the lab, water has a density of 1 milliliter for every gram of water. So we would express that in terms of density as 1 gram per milliliter, since density is grams divided by milliliters. But all that's really saying is that every milliliter of water will weigh 1 gram on the mass balance. And so we can use that to our advantage, understanding that whenever we pour in 1 milliliter of water into one of our cups, we're really pouring in 1 gram of mass. And that allows us to carefully control exactly how much mass we're pouring in to that side of the mass balance, rather than having to use clunky standards of measurement like coins, where we can't really control how much we're putting in at a time. It's much easier to control the volume of a liquid than it is, solids like coins for a standard unit of measurement. So let's see how this is going to play out as I demonstrate weighing out and taking the mass of a roll of electrical tape, using water as a standard unit of measurement. The first thing I'm going to do is place my electrical tape into the left side of my mass balance. I have nothing in the right-hand side at this point in time. Now I'm going to take just something I might have lying around at home that weighs volume in any form. This could be cups, teaspoons, ounces, or even milliliters. And I'm going to just fill it up with enough water that I think is going to be sufficient to equal the mass of my electrical tape. And now I'm going to go ahead and start gently pouring in, carefully, water until my mass balance starts to move. And I know I'm getting close to equaling the volume of my electrical tape. Or excuse me, I'm equaling the mass of my electrical tape. Now that I know I'm close, I'm going to just add my water in dropwise until I get the perfect mass. Now I know it's balanced. So the mass equals the mass of the electric tape in water. I guess I felt like I needed one more drop. now the two masses are equal. So I know the mass of my water on the right equals my mass of my electrical tape on the left. So I've made sure my measuring apparatus is dry. Now I can take that volume of water, which I know equals the mass of my electrical tape, and pour it into my measuring device. Now sometimes our measuring devices won't be adequate. My measuring device here, I look and I level it out and I realize that the volume of water present I can't measure because my graduations don't even start with this little amount of water. So I have to turn to something else. Well, a teaspoon will do. So with this 1 teaspoon measuring spoon, I simply pour out quantities of water into my teaspoon until I fill it up. And I keep doing this until I get the proper number of teaspoons of water that are present in that quantity of water. And if you've been counting, we're on our 7th teaspoon here. Eighth. And it just worked out so it was a perfect 9 teaspoons of water. And now we know exactly the volume of water that was present that equals the mass of our electrical tape. And we can use that to figure out the exact mass of our electrical tape. So how do we use this information to find the mass of our electrical tape? Well, we know that our roll of electrical tape's mass is roughly equal to 9 teaspoons of water. What we need to know is the mass of 9 teaspoons of water and convert that to grams. Well, we already know one conversion factor, which is 1 milliliter of water equals 1 gram of water. Well, now we just need to look up another conversion factor, which is how many teaspoons are equal to a milliliter. And we can use dimensional analysis to solve the rest. So when we look up how many teaspoons are in a milliliter, we find that 1 teaspoon equals exactly 4.92892 milliliters. With these two conversion factors, we can set up a 2-step dimensional analysis problem and determine what the mass of our electrical tape is. So in our first step, we write out what we're converting from, which is 9 teaspoons. We know that the 1 teaspoon goes on the bottom from our first conversion factor, and we need to first convert to milliliters of water. 1 teaspoon equals 4.92892, so that goes on the top. That will help us to eliminate the teaspoons and get us to milliliters. We can then cancel out our teaspoons units and then move to our next conversion factor. Milliliters needs to go away. We do this by using our second conversion factor. 1 milliliter equals 1 gram for water, and that's the density that we're using as a conversion factor. This will allow us to cancel out the units of milliliters and get us to grams, which is what we want. We then cancel out the milliliters and make sure that we set it up properly, double checking our work, making sure our conversion factors are appropriate. And now we can move on to the next step, which is simplifying our expression and doing the math. When we get rid of everything that's unnecessary and we simplify the expression, we're left with a simple multiplication problem. All we have to do is multiply 9 times 4.92892 in grams, and we end up with our final answer. When we do the math, we'll end up with 44.36028 grams. Now, there's a next step that we'll take in the future, and that will be to round this off to 1 digit, which we will call 1 significant digit. We've learned a little bit about significant digits, and there's a reason why we do this, but we'll get to that later. The proper way we would express this is as 40 grams. But at this point, we'll just stop there and understand that if you were to put 44.36028, that's okay at this point. But that's the way that we would use water for our mass balance. It's a much simpler way, if you actually think about it, to get a more accurate measurement at home. And so this is what we'll use from this point forward instead of coins.